So this radial velocity method has been a great triumph. At last, we found huge numbers of planets around other stars. The people who did it became famous household names. They write books. They get huge amounts of telescope time, all the good things in life. And these weird things we're discovering. We're not finding anything like our own solar system. We're discovering these hot Jupiters and these eccentric giants.
So, Paul, whenever we measure things, we always have the inclination, right? So if it, we're throwing a lot of a faith in the idea that we're really getting a random selection of stuff. It strikes me that we would really like to pin down that inclination a bit better.
I mean, that's one worry about the solar system. For any given planet, we don't know the inclination, so the mass could be much bigger than what we're talking about. So when we talk about resonances in Upsilon and Andromeda or whatever we're talking about, maybe we're talking complete crap because they're actually, in that particular system, they're nearly face on giant stars. The other thing that really bugs me is that we're not actually sure these things are planets. All we know is a mass and an orbit. I mean, it could be a black holes orbiting, or, I mean, who knows what it could be. Huge alien space civilizations, or what. It would be nice to actually know we're talking about planets here.
So, Paul, why don't we think about doing what Captain Cook did when he was on his way to explore Australia? He, as you recall, was actually employed not to look for Australia, but to look at a transit of Venus. And the idea was back then is if you could see the planet Venus go in front of the sun, you could quite accurately measure the distance to the sun, which back in the 1700s was not well known. And so Captain Cook, of course, that was the things he did, and in an interesting twist of fate, the science subsidized the military outcome afterwards, which was to go out and essentially claim Australia for England.
Yes, we always tell us when politicians ask what uses astronomy, we say, well, it does have spin-offs like Australia. In the case of these extrasolar planets, we're not going to actually see the dot as it goes across here, but we won't, because bear in mind that we're not seeing the disk of the star, we're just seeing a
It's
single
just a
blurry
little point of light, right?
Yep. But what we could tell is as it goes in front, we get the dip in brightness. It's only going to happen if the planet's in an edge-on orbit. So is that likely at all? Well, some fraction are going to be, quite a small fraction. If the
Certainly
planet's
those
pretty
hot
close,
Jupiters are going to quite likely be.
they've got quite a good chance that it'll be. Of course, bear in mind this is not to scale. The planet here is actually much too close in to be
Right,
realistic
they're not
to
nearly
scale.
as big.
But if it's much further away, it could be edge-on. So what a bunch of people did was they went out and looked at all the planets which we knew from radial velocity had planets, or so we thought, and they were hoping that maybe one or two of them might actually by a fluke be edge-on enough that we could see the transits.
So this is a great experiment, right? So a young astronomer named Dave Charbonneau literally went out with a tiny little telescope in the parking lot of his university and stared out at one of these stars with the very sexy title of HD 209458, and this is what he saw.
He knew when to look for the transits, because from the radial velocity you could work out exactly when it's going to pass in front. And here's the brightness. So 1 is the normal brightness, and you can see it dropped to by about 1.5%. Wow. As at the right time. And then he observed again, and it did it again.
Wow. So this is a great idea, because if it's going directly in front of the object, we know the inclination exactly. It's effectively, sine I is 1 to as good a precision as we need, and so there is no ambiguity.
So let's see what we can work out from this data. Okay, so what can we deduce from a transit like this? What we know is that the observed brightness against time goes down. So what we can measure is how long the transit goes for. Let's call that, say, delta t, and the change in brightness, delta b. And we can also measure the normal brightness of the star when it's not in transit, b. What can we learn from that? Well, the easiest way to think about it is to imagine the disk of the star, which is all glowing. And from our point of view, every bit of the star will have about the same amount of glow. We won't actually see the star, it'll all be a point, but nonetheless we're getting a contribution from this bit, a contribution from that bit, and so on. But now, something dark has moved in front of part of it, which means we're losing the amount of light coming from this bit. Now that's got a radius r planet, as the overall thing has a radius r star. So the fraction of the light we're losing, so fraction of light lost, is going to be, well, let's call that delta B over B, is going to be the fraction of the star surface it's blocked from our point of view. So that's the area of this divided by the total area, which is pi rp squared all over pi rs squared. So the pi's cancel. Equals radius of the planet over radius of the star squared. We need to rearrange this because what we actually measure is this, and what we want to know is radius of the planet. So take the square root of both sides, and we end up with rp equals radius of the star times the square root of delta B over B. Now this is assuming that all parts of the star have the same brightness as viewed from us. In practice, the edge bits of the star appear a little bit darker. It's called limb darkening. So a proper model would have to take that into account. But if you measure delta B in the middle of the transit, this is actually pretty accurate. So, what's the radius of this particular planet? We have delta B is 1.5%. In this particular case, we know that the radius of the star is 1.1 times the radius of the Sun. So in this case, the radius of the planet equals 1.1 times the radius of the Sun, which is 700,000 kilometers. Close enough. Times delta B over B, it's 1.5%, so that's 1.5 over 100, the ratio, which comes out as about 94,000 kilometers, which compared to Jupiter, which is about 70,000 kilometers. So it's looking like a gas giant, a bit bigger than Jupiter in fact, but roughly comparable. Now that's the simplest thing to work out. Just look at the dip in brightness, divide by the normal brightness, and that gives you the ratio of the sizes. You can also, if you look at the brightness versus time, and if you see more than one transit, you can measure the orbital period. Might be from the middle of this transit to the middle of that transit. And we've already derived the equation for this, that the orbital radius, how far the star is from the planet, is equal to the cube root g m star period squared over 4 pi squared. Now in this case that was already known from the radial velocity measurements, but if we discover something purely using transits, that's a useful thing to be able to work out. A final thing we can work out is to get the exact inclination. We know it has to be nearly edge on, and that's usually good enough. But if you think about it, here's the disk of the star. Now from our point of view, the planet's moving across. If it's exactly edge on, it's going to go at velocity v across there. So the transit time will be delta t is going to be 2 r star over the orbital velocity of the planet. But if it's slightly off edge on, then it's got less distance to cover, and in principle you can have a glancing transit where it's got be very, very short. So you know the angle inclination is nearly 90 degrees, but you can work out exactly whether it's 87 degrees or 85 degrees or something like that by looking at the delta t. You know the orbital velocity from the radial velocity measurements, or you can calculate it from this. won't do this calculation. It's a bit complicated and fiddly, but this gives you the exact inclination. It doesn't really matter too much because it's going to be nearly 90, but it's sometimes nice to know.